This is the last set of slides for topic 2, and in this set we're going to talk about uniform circular motion. And uniform circular motion is just like the name sounds. It's circular motion that is uniform. And in order to have uniform circular motion, or what we'll refer to as UCM, we have an object that's traveling in a circular path at a uniform speed. And if something's traveling in a circular path, as we know from math or geometry, as it follows that path, it's constantly changing directions. And there's no point along that circular path where it's traveling in a straight line. We can analyze motion at a tangent to that circle at any given point, but at no point is it actually traveling in a straight line. And so as it's moving around, the magnitude of the velocity, which we now know is called the speed of an object, is constant, but because the direction is changing, the velocity is also changing. And remember that velocity is a vector, so the direction of motion does in fact matter. And if we draw ourselves a little circle, we can easily see this. If we have an object traveling counterclockwise, so in this direction, at this point here on the right, it's traveling in this direction. By the time it gets to here, it's traveling to the left. By the time it gets over here, we're traveling down. Comes over here, we're traveling to the right, but only for that particular instance. Now, a couple terms that we need to be familiar with when we're talking about circular motion. The first is frequency. And the frequency is how many times does the object follow or get around that circular path per second or per unit time. And our frequency is measured in hertz. And we're going to see this term hertz come up again when we're talking about frequency related to waves, especially things like radio waves and microwaves. But it refers to the number of cycles or the number of events occurring per second. In the case of circular motion, it's revolutions or times around the circle. So 1 hertz means that it takes 1 second for the object to move around that circle completely. The inverse of the frequency is what we call the period, and the period is the time it takes for 1 complete revolution. So if it takes 1 second for an object to travel in a circle, that means that its frequency is 1 and its period is also 1. If, on the other hand, an object can travel around a circular path in half a second, its period is going to be 0.5 seconds, but in that 1 second it's going to travel around the circle twice, so the frequency is going to be 2 hertz. So our equations are pretty straightforward. The frequency is 1 over the period, and period is 1 over the frequency. As we mentioned, the speed or the magnitude of the velocity in uniform circular motion is constant. That's where the uniform part of the name comes from. The speed is uniform, and when we're talking about circular motion, the distance that we're talking about is the distance around the circle or the circumference, and we know that we find the circumference of a circle using 2 pi r, and we'll see if we can write this in the space provided. We're running out of room. Anyway, circumference. So 2 pi r is the circumference. That's the distance we're dealing with when we talk about circular motion, and the time is the period. So our speed in uniform circular motion is 2 pi r over t, where r is the radius measured in meters and t is the time measured in seconds. And that gives us units of meters per second, just like all of our other speeds. Now realize though that even though the speed is uniform, because it's constantly changing direction, the velocity is constantly changing. Because the velocity is constantly changing, that means the object is accelerating. And again, here, related to the fact that the speed is constant, that means that it's traveling around the same portion of the arc of the circle in any given time, which means the velocity is changing at the same rate, which means that the acceleration is also uniform. So we have uniform speed. We also have a uniform change in velocity, which gives us a uniform acceleration. This acceleration is given the term centripetal acceleration. And centripetal just means towards the center of the circle. So our centripetal acceleration is towards the center of our circle. And so you can see in our diagram here that the acceleration right here is towards the middle. This is the middle. And our speed, or our velocity at this instant, is downward. Our object here is traveling clockwise, and so at this point where this red ball is, the speed and the velocity are both, or the velocity rather, is downward. The speed again is uniform. We calculate the centripetal acceleration using v squared over r, and there's a derivation we can work through to solve for why it's v squared over r, but at this level you don't need to know that derivation. Just understand that centripetal acceleration is v squared over r, where v is the speed of the object and r is the radius. And again, of course, just so there's no confusion, the radius is the distance from the center out to the edge of the circle. Generally, our speed is measured in meters per second, our radius is in meters, and our centripetal acceleration is in meters per second squared. And the reason for this is because since it's v squared over r, that's meters per second squared over meters, which gives us meters squared per second squared over meters. Cancel out, cancel out. We're left with meters per second squared. Now we can also look at the acceleration in terms of the radius and the period of travel. And so let's look at our velocity equation, which, as we just mentioned previously, remember, velocity is 2 pi r over t. And if we square that whole thing, we get v squared equals 4 pi squared r squared over t squared. Now, the reason we do that is because if we remember from the previous slide, our acceleration equation is acceleration equals v squared over r. So we're going to take our v squared, plug it in. So a equals v squared over r. We're going to take our equation for v squared, plug it in here, and what we end up with is the acceleration is equal to 4 pi squared r over t squared, because our r, one of our r's on the top, cancels out with our r on the bottom, and we're left with acceleration is 4 pi squared r over t squared. And so now we have it in terms of radius and period rather than velocity, or speed rather, and radius. And so again, depending on the situation, depending on what measurements you're making or what data you're given, that's going to impact what calculation or what equation you use. Now, the next step in this then, since we have acceleration, that means that we must have some net force. As we learned previously, in order to have acceleration, we have to have an unbalanced force or a net force. In this situation, we call that force the centripetal force. Again, just like we had the centripetal acceleration is caused by the centripetal force, so it's pretty straightforward. But understand that this is not some new magical force. This is simply an application of all of our other forces. Any of our generic forces that we've talked about can act as a centripetal force. The force of gravity keeps planets in orbit in the solar system. That force of gravity is acting as a centripetal force. When you drive around a road, a curve in a road, there's friction between the wheels and the car, or the wheels and the road rather. That friction is acting as a centripetal force. If you swing a yo-yo around your head on a string, there's tension in that string that's acting as the centripetal force causing the yo-yo to accelerate in a circular direction or move in a circular path with acceleration along the line of the string. So centripetal force is not a new force. It's simply an application of all of the other forces that we know of. And we calculated it essentially the same way. Force is equal to mass times acceleration, just like it was before, and this comes straight from Newton's second law, right? This is our second law equation. We're going to make that into an A. Okay. But in this case, we have a specific acceleration. The acceleration is centripetal acceleration. And so we're going to take our centripetal acceleration, which is v squared over r, plug that in, and we get F equals mv squared over r, where m is the mass of the thing moving in the circular path, v again is the speed of the object, and r is the radius of its path. And if we just look at this kind of briefly, in order to keep an object moving at some speed, at some radius, if we increase the mass of the object, we need to increase the force that's being applied to keep that object in that circular path. So there's a direct relationship between the mass and the force required. With the speed, there's another relationship there, whereas the speed increases, the force then increases proportional to the square of the speed. And then there's an indirect relationship between the radius and the force. As the radius goes up, the force required to keep the same mass moving at the same speed goes down. And the reason for that is because the magnitude of the acceleration decreases. Okay, so let's look at a real quick diagram of circular motion. Here we have some object that's moving in some circular path clockwise, and at each of these given points, the purple arrow is indicating the direction of the velocity at that point. The green arrow is pointing towards the direction of the acceleration. Notice that the acceleration always points towards the center of the path being described. It's always moving towards the center of the circle. And the velocity is always tangent to that circle. So there's always a 90-degree angle between the velocity vector and the acceleration vector when we're talking about circular motion. There's always a 90-degree angle between the velocity and the acceleration when we're talking about circular motion. The force and the acceleration are always in the same direction. And remember, this is straight from Newton's second law. The direction of acceleration is always in the direction of the net force. When we're talking about circular motion, the net force is towards the center. So the acceleration must then be towards the center of the circle. You've experienced this phenomena all the time, this idea of circular motion, and many times you've perhaps heard it referred to as centrifugal force, which is not completely accurate. There's no force that's actually pushing you out. Think about when your parents drive around a curve too fast and you feel like you're being pushed up against the door, or you're in a roller coaster going around a curve and you feel like you're being pushed out to the side. It's not a force that's actually pushing you out. What's actually happening is there's a force pushing you in. As that car with you in it and somebody else goes around the corner, your body wants to travel in a straight line. Your body's inertia, that probably wasn't the best color to pick, your body's inertia wants to keep you going straight, but hopefully you're wearing your seatbelt, and hopefully the car door is closed. And as you're traveling around this curved path, the vehicle is actually pushing you towards the center of the circle that's partially being described by the curve. And so you're not being pushed out, you're actually being pushed back in so that you follow the path of the circle that the rest of the vehicle is following. Now, just to give you another example of this, if any of you have ever been to the fair and ridden the Gravitron, which is a super awesome ride if you've never ridden it, maybe has some other names. Anyway, it's basically the UFO, I think. It's basically this big spinning disc that you get in, you stand up against the wall, and they just start spinning the thing as fast as it'll go. Great ride, great example of circular motion and centripetal force. And so let's watch a short video of how this works. So here, the ride's already started, and so these folks are already kind of up on the wall, and let's take a look at it. And you can see the two girls kind of over here were up against the wall. They're way up, and then these guys over, yeah, here we go. Oh, this guy's all over the place. Let's pause it. So you can see these two girls right here are about 2 feet up in the air. Remember that, or if you've never been on it, you're standing straight up. These pads along the wall are basically straight up and down, and you stand against them, and the ride starts to spin, and slowly they drop the floor away. And what's happening is the ride gets you moving in a circular path so fast that your inertia is pushing you up against the wall. And your inertia is pushing you out, and as it's pushing up against the wall, there's a force there of the wall pushing back on you. Anytime you have two things in contact, you have frictional force. And in this case, the ride's going so fast that the forces between you and the wall creating friction are much greater than the force of gravity that would normally be pulling you down. And so the frictional force overcomes the gravitational force, which is what holds your body up. And so let's watch a few more minutes here, a few more seconds. Wow. And you see these guys are even sitting up and down or upside down. And so that centripetal force, in this case, their inertia is pushing them out, and the centripetal force is coming from the walls of the ride. The walls of the ride are pushing in towards the center of the circle. They're pushing in on all of these kids that are in this ride, pushing them back around in this circle, while at the same time their body's inertia is trying to carry them in a straight line. If you've ever swung a ball on a string and then let it go, as soon as you let it go, it stops traveling in a circular path and starts traveling straight because you've removed that circular force, and so it's, or that centripetal force, so its inertia is going to carry it in the direction that it was going at the instant that it was released.